cycle de séminaire à SystemX. Et on est ravis aujourd'hui d'accueillir Marios Kountouris. Alors, Marios Kountouris est professeur au département des systèmes de communication d'EURECOM à Sofia. Et puis, de façon peut-être un peu rapide, ce que je pourrais dire, c'est qu'il a démarré des travaux de recherche maintenant depuis un petit moment. Il a commencé par des activités côté Université technique nationale d'Athènes. Et puis après, il est passé à Télécom Paris, où il a passé une thèse. Et puis après, il a occupé de nombreux postes, hein, aussi bien en entreprise qu'en établissement public. Supélec, Université de Texas ou également Université en Corée, hein, à UNC. Et puis, il a aussi passé du temps chez Huawei. Et maintenant, il est à EURECOM, donc à Sofia Antipolis. Et dans le cadre de ses travaux qu'il mène, et dont il va nous donner un petit aperçu, il a pu recevoir une bourse ERC. Donc, c'est quand même assez notable parce que pour la structuration de la recherche, ça impose et ça structure beaucoup les travaux. Donc, une bourse ERC sur les communications sémantiques orientées vers les objectifs. Et il est par ailleurs très actif dans l'association I3E en étant rédacteur en chef de plusieurs journaux, Wireless Communication, Signal Processing, Signal Communication Letters. Et puis il a reçu de nombreuses distinctions. Je ne veux pas toutes les citer parce qu'il y a beaucoup de gens qui sont intéressés à tes travaux. Dernièrement, la médaille Blondel de la S2E, mais des prix comme SOC, enfin, I3E comme SOC ou Signal Processing Magazine, Globecom, etc. Bon, en tout cas, pour aujourd'hui, il nous fait le plaisir d'être parmi nous pour nous présenter ce sujet des réseaux sémantiques, Goal-Oriented Semantic Communication for Distributed Edge Intelligence. Bon, c'est un sujet qui, pour nous semble relativement d'actualité. Alors, on n'est pas les plus sachants sur le sujet, mais je pense qu'il y a pas mal d'acteurs de la recherche qui s'intéressent à cette dimension sémantique. Et enfin, Marios nous en parlera mieux que moi. Je vais lui passer la parole pour donc une intervention que l'on va essayer de faire tenir dans l'heure. Il y aura des questions. Je vais lui laisser gérer les interactions avec les participants, qui peut être au fil de l'eau. Si vous avez des questions, vous pouvez peut-être lever la main. On n'est pas trop nombreux, donc ça peut peut-être se gérer comme ça. Mais sinon, il y aura du temps à la fin de l'exposé pour présenter éventuellement des questions. Et enfin, je vous demanderai effectivement de lever la main pour qu'on puisse organiser les prises de parole. Voilà, ben, je ne vais pas en dire beaucoup plus. Marios, je te passe la parole pour cette présentation. Je crois que tu l'as fait en anglais, hein, tu m'as dit.
Oui, d'accord. Merci beaucoup, Patrice. Merci pour l'invitation. Merci aussi pour l'introduction. Oui, je vais faire la présentation en anglais, mais après les questions, si vous voulez, on peut le faire en français. Il n'y a pas de problème. Juste, ça va être un peu mieux en anglais. Et je vais la garder aussi un peu comme un tutoriel. Après, si vous voulez des détails techniques, on peut entrer dans les détails. OK. Donc, je switch en anglais. So, yeah, I'm going to present actually what is the topic which has become a bit it has a certain momentum these days, this goal-oriented semantic communication, which is where I wrote my ERC, Consolidated Grant, I wrote it 2019, submit 2020, where back then there were very few people discussing these ideas. There were hardly any technical paper. I'm trying to motivate the topic, see why we need it, what is the definitions and all that stuff. And then we will continue with some technical frameworks and some technical models and some scientific things that we will need. So let's start with, okay, it's a topic on communication. So it would take some kind of engineering perspective. We're entering the era of 6G. There's a lot of discussion, vision papers. And towards 6G, there are different views, but there's some kind of consensus, although it's very, very large. So we will have new services and use cases. People are becoming, some people very, very aggressive or imaginative, futuristic about we're going to have these digital twins. We're talking about the metaverse, but also there are all these societally beneficial applications like the telepresence, telehealth, consumer robotics, and so on. And for that, there's different standardization bodies and organisms that are trying to define, to say what is the key performance indicator, the KPIs. And there is a lot of technology enablers. Basically, we're trying to take what we have done for 5G and bring it to a different scale. So MIMO and massive MIMO. Now we'll talk, probably some people are discussing about large intelligent surfaces. Some people in the beginning, at least, they were very excited about going to higher frequencies like terahertz. Now there's more skepticism as well. There's the joint sensing communication, integrated sensing communication appearing. All these ideas are around for a few years and they have been discussed. What is for sure is that now wireless communication, wireless systems are not by themselves anymore. We have data and machine learning and AI there. There's a data analytics as well, but also there are many key applications actually of machine learning for communication also what communication could do for bringing machine learning into a network. And there's a bunch of sensors. We're talking about this IoT, which is mostly like a 5G thing, the Internet of Things. We're going to have a lot of devices which are not that simplistic anymore. We're going to have sensing capabilities, going to have good processing capabilities, could do some machine learning things. That's for sure. It's going to be there. And now we're going to see things merging. So we're not talking only about communication, but we're talking about sensing, because this is how we're going to perceive actually the reality and the environment and do certain things. We're going to have the computation aspect. We're going to have AI native networks and so on. There's going to be a continuum of these things. And definitely the new generations are not going to be just for, improving our video and the telephony. And this is basically more or less the evolution. So we have from the 2G that we start with voice and going all the way to video conferencing, mobile internet. And let's say 5G, most people will say this is the wireless for things, the Internet of Things. So the big question now is like what 6G is going to be. Is wireless for what or for whom? And for that, let's take a fast forward to, let's say, a few years later, 2030 or more. And what we see basically the emergence of a lot of cyber physical and mission critical systems. There's a lot of interactive systems. There's a lot of autonomous systems.
لكن تحب تحط بصمتها على السلايد ببهام.
Excusez-moi,
Sorry?
il faut... Non, je crois qu'il y avait un micro qui était ouvert. Je crois, Anis, il faut que tu penses à fermer ton micro. Merci.
D'accord.
دافيد يعرفك انت يعرف السلايد نتاعك.
Anis, je vais fermer son micro.
D'accord.
Oui, peut-être qu'il faut intervenir.
Voilà.
Okay. Merci.
Excuse-moi.
So we're going to have all these cyber physical systems and these autonomous systems. Let's think about swarm robotics, self-driving cars, smart, intelligent Internet of Things. And we're going to have all these things that they will, and actually wireless communication, the future systems will have to cater to this kind of cyber physical systems. So we're going to have all these network intelligence systems, whether these are small sensors, cars, or even, smart base stations. And they'll have different needs now. We will need some kind of reliable real-time communication. The notion of real-time, it's something that will appear more and more, but then we have to define what is real-time. I'll talk about this later. We're going to have a lot of interactions, and this will be autonomous. So we don't imagine things that scale, like self-driving cars scale when they have to be base station control all the time. We may have a bunch of robotics or a platoon of vehicles navigating into the city. So they will have to communicate, exchange information, and autonomously operate, not to mention they'll have to do some decision-making, which has to be also be done on a timely manner. So for example, imagine a bunch of cars trying to navigate into the city, each one having its own radar, cameras, and so on for, accident prevention and pedestrian detection. So they will exchange information. So they have different views, let's say, of the street. So imagine that these cars, they have to do some kind of collaborative thing, like a collaborative maneuver. So they will have to arrive by exchanging information. They will have to arrive in a timely manner in a certain consensus. So that's one of the things that and that's one of the claims as well, that if we keep doing things, if we keep communicating the same way we're communicating, let's say for, I don't know, video, or for, watching Netflix on our mobile phone, things might not scale much. And on the top of that, we have a lot of on-device and in-network computation. Okay, so wireless communication will be the foundation of that system, that they will need different kind of communication, will have different requirements. So we're gonna go from the, let's say, connected things to the connected intelligence. So once again, and this is good for people doing communication, the wire network are under pressure because they will have to provide certain extreme requirements to different kind of systems. So the challenge will be like we have to process and transport massive amounts of data. Imagine having a lot of sensors and all these Internet of Things in a bigger scale. They will generate a lot of traffic, and they will have to send it somewhere for processing, or even locally, or even in a bigger thing. Imagine sending things on a cloud or on the edge to process. We have extra constraints. We have applications that require processing and decision making on a real time, but of course we have to be careful about the energy, security, and privacy all the time. And all the data are not simple. We're not just like voice video. That's quite optimized, actually, the network for that. We're going to have multimodality. We're going to have high-dimensional data, a lot of rich content. And on the top of that, it will be geographically distributed, not to mention that now the users are the data owner, and sometimes we don't even have access to that. We might have, like, think of a federated learning. So that makes us some scenario, even on an industrial scenario, when you have like small sensors collecting information and sending it to the cloud, you can easily arrive to things like few terabps actually that you need to provide in certain applications. Not to mention the autonomous cars when they collect all these things with radar is a simple thing, but images, video, and so on. So now the big question is that, okay, we envision this kind of application. We envision this futuristic work. We envision about this metaverse, or like doing this digital twin. I want to reproduce exactly what I'm doing now. I want to reproduce myself, I don't know, in Japan. We know the requirements. Now the big question is, do we know how to do it? Do we have the right theory to do it? Do we have to just do a small evolution of the existing systems, or we need a radical departure? And this is where things start now for the semantic communication. Let's see what we have done so far. So we go back to the theory, and of course, the credits goes to Shannon, where basically he described the fundamental, the most impactful, actually, communication model, which back then the problem was the noise, basically. So it was a problem of reliable transfer of information. So I have an information source, and what's the problem? I want to reproduce as exactly as possible, with no errors, the entire information flow that the information source has into the destination. Okay, so then the transmitter does the encoding, and there's a channel that introduces the noise. It's a statistical model, and it was the right approach to solve the problem and have all these successful applications today, going from the compression thing, but also from the communication. Now, in his seminal paper, he did something, what we call a master stroke, basically, because he said, okay, let's leave semantics out of the picture. So I don't care what I transmit. I don't care what the packet, what's the meaning of the content I have, or what is going to be the impact, the effect of the destination. What I care is just, for me, it's like, let's say, random bits. I just want to reproduce them with no errors at the other side. Because the problem was noise back then. And that was actually the right thing to do back then, not only because the first problem was the noise, it was an engineering problem, but also because it became complicated, actually. And this is what we're trying to even touch these days. And it's really complicated, actually. The other thing as well that sometimes we forget is that the encoder and decoder are normally jointly or centrally designed. Where now, if you imagine now different systems entering and they have to communicate with each other, they might even have, I don't know, even different versions of software could violate this kind of assumption as well. And so now things are not that controlled as possible. Okay, that was the theoretical foundations, a success story. And people took that and brought it into practice. So this is the theory that would make us design the networks. And now my claim is that the way we evolve into the generations, the way we go into designing the 5G and now 6G, I think we're gonna try, I mean, most vision papers, at least in academia, are trying to do that thing, is this kind of what we call maximalistic approach. Okay, I don't know, take the rate, multiply by a factor of 100 or 10, or depending on what kind of KPI you have, just provide some inflated requirements, and this is the way to go. Okay, so basically we try to boost the things, and the way to address all the signaling of the metadata we have to do, normally we do over provisioning, also the resource allocation and so on. So the claim here is that if we keep going like that, it's something that is not going to scale meaningfully. It's also, it won't be even able to probably guarantee the real-time requirements we have, the timely decision-making and so on. Okay. Of course, back then, Shannon, actually, Weaver was actually, I think his boss back then, his manager in Bell Labs, did an introduction on Shannon's similar work and say, okay, he envisioned that, okay, Shannon's basically was what we call the engineering problem, the technical problem, how to accurately transmit the symbols from the transmitter to the destination. Now, there are two other levels, the semantic level, that what is the meaning of the transmitted symbols, and what some people call level C, the effectiveness problem, or some people call it pragmatic. What is the effect, actually, how the destination will change its actions based on the messages. That was an introduction. It was a wishful thinking, and people have tried to build theory on that with some honorable tries, but who never had any theory that will have an impact. But I think now is the time to start looking at these questions. Now, I put here the semantic with the meaning and so on, because this comes from linguistics, but then I will define what I mean semantic. And there is a lot of, let's say, debate these days about definition and so on, but as long as we define things, it doesn't matter how we name them. So let's see a high-level change of the model. So in the traditional model, what we do is somebody give us traffic. So traffic is exogenous. We don't even care who generates the traffic. We don't even control the data generation. For a communication engineer, the traffic is just a sequence of random bits. Okay, we don't know what they present. We don't know why we deliver on the other side. For it, we have a pipe. So the physical layer, the transmission, the transport, all that stuff for us is like just an opaque data pipe. And normally people also in the industry, what they care is that the pipe is fatter and fatter. This is what we care. The rest is secondary thing, because it's the applications that will decide that. And normally the way to optimize is we want the reliable transfer, so we have metrics like throughput, error rate, some delay, some QoS. But that's basically how communication engineering works, up to a certain abstraction. So what the goal-oriented semantic communication model tries to bring here, first of all, we start all the way from the beginning, so from the generation of traffic. And the biggest claim is that all these things is a joint, a non-separable design of the whole life cycle of communication, which goes from the data generation, the transmission, and the reconstruction for certain users. Okay, so first of all, we need to be able to control the data generation. We need to generate at will. When, for example, certain messages have to be transmitted or not. And I will come back to that, why it's important. Then in the processing as well, we need to do some kind of filtering, some kind of censoring. And then this goes all the way until the end of the transmission. You can have also in the medium access some kind of preoccupation. How do we do that? Through the semantics of information, which I will define a bit later, but here's the importance of the message we're trying to submit, not the meaning. Okay, so we have, let's say, a goal. We want to communicate. Communication is not an end in itself. There's a goal to do. Some people call it task-oriented. You can see it as a smaller subset of that. So I want to communicate because I want to do something. Okay, I want to send packets to somebody else because, you know, there's a task to be performed. There's a certain goal to achieve. Given that goal, certain packets or certain messages will be more important or more significant or more useful than others. So not all bits are equal now, okay? So if I can do that, if I can take this into account all the way from the generation, when I see the phenomenon that I have to describe, let's say, I want to do some kind of representation of a physical phenomenon, and I'm the sensor that I'm doing some sampling, I'm checking certain things. If I know what I'm interested in, I will not send whatever content I want. So take an example, for example, it's a camera during the night. What I care is just to see whether there's an intruder inside. So uniformly sending, I don't know, dark pictures, black pictures, all the way there just to say, okay, there's no alarm, business as usual, and so on. It's a waste of resources, a waste of energy, waste of something. And then if I really need to, and if I share the medium as well, I'm taking some opportunities from somebody else. And if I really need to communicate something critical, then I might not have the resources to do that. So maybe if I know why I care, why I do this images taking or video taking, then I could optimize things all over the place, okay? And this is what goal-oriented semantic communication is trying to do, okay? It has a connection also with some kind of multi-agent communication, because now we have kind of a two-way systems. So it's not like, okay, source is sending a message to the destination and we are done. If you think as a general as an agent, so the state of the agent, we're having a state changing functions where the state of the agent will change, and this will create something else. So probably the agent would then send another message to the source and so on. And we have this kind of scenario. We're going to have different things between like push-based communication and pull-based communication. And this is because of the decision making. And this, under these kind of general models, we can actually put various scenarios of interest. Either whether it's for control, when I do remote tracking, when I do remote actuation, or for some function computation, some sensing, SLAM, multi-view cameras, for example. All of these scenarios could be modeled with this kind of communication things. So let's go now to the definition of semantic information. We have been a big debate. I mean, people now have chosen their own camp, but I will tell what I have defined in the ERC and what other people back then were discussing. And for us, semantic comes from the etymological meaning, which is important, significant. So in ancient Greek and actually modern Greek, and I'm Greek as well, so I can tell you, you can believe me as well. Semantic is still important. It's from semantikos, okay? So we define semantics differently than what people use in the linguistic, I don't know, for whatever reason. We define it as the significance, the importance, and it has to do with the effectiveness as well. And the way to define it, because one of the biggest problems we had is, what is the semantics of information? Okay, we want, for example, to quantify how important is the message. How do we define that? So Shannon, when he had to do the cooperation and the communication, he had the entropy of the source, the guide, because that was the quantity of information. And that was brilliant, and it worked. Now, the problem starts like, how do we measure that? And I could say that we have different tries. We have different kind of definitions. We're still lacking that. And as long as we don't have a very crisp mathematical definition, we won't be able to build a nice theory. So our vision was like, let's define the semantics of information in different granularities, in different resolutions, let's say. So the first one is what we call the microscopic one. It has to do with all the way to the source, okay, where the message is generated, when information is generated, actually. And this has to do with the relative importance of different outcomes or events. So given the application, given the goal, given what the end user wants, different outcomes could have different interest or impact to the decision. The typical example is like, even if we have two rare events with the same kind of probability of occurrence. So the more rare the event, the more information is going to transmit it according to the entropy. Then suppose that we have that, okay, I don't know, it's gonna snow in the Sahara Desert. For most people, it's like, oh, cool, okay, good news, but we're not gonna change something. But if I tell you there's a very rare phenomenon that, back in your house now, it's going to be a catastrophe and you have to go and protect your house, I think nobody will follow the talk. Okay, everybody will run. You might have the two events with the same kind of low probability, so the same kind of entropic content, okay? But you have completely different actions when you receive it. So the importance of these two icons are different, okay? The relative importance. And this, of course, depends on the receiver, on the observer. So now the observer, the end user, or the application are becoming back the king or the queen. And on the top of that, is that things are relative because it depends on the application or the context, let's say, of users. So everything depends on what you want to do. Okay. Now there's another level, the mesoscopic, which is more the, I would say, the engineering approach, when we have to define what is the semantics of information in a leak level or a network level. This is what will allow us to solve some problems. Okay. And I will talk a bit later. And there's the microscopic one, because at the end of the day, what we're trying to solve here, the fundamental problem is like there is information, there is an event, there is a phenomenon generated at a certain point at space and time. And what I want to do is I want to reproduce it in a timely manner, basically, at some different point of space and time. So you could see it as a macroscopic kind of end-to-end information transfer, which then this abstraction will allow us to solve some different problems. I'll have a slide at the end. Okay. Now, most people say, okay, semantic is meaning. So there's papers now that, okay, they try also to do semantic communication with meaning, NLPs, and so on. So what about the meaning? Now, people have tried, actually in the beginning, have tried to build what we call semantic information theory based on meaning, okay? Starting from Karnam Bar Hillel, fundamental paper, seminal work, and so on. And people have tried to do that. Now, apart from the fact that it's very difficult to find a theoretical framework, there's a lot of paradox and so on, there's even different problems. The first one is, even if you try to define some semantic similarity on messages and so on, even to minimize the average semantic error, it's an hard problem. Of course, we say, okay, there's no big deal, we're gonna compute, but we cannot do many things in theory. The same way, you know, Shannon optimize. With Shannon theory, we could optimize. There's a lot of approaches having to do with, doxastic, what we call the doxastic sciences, theories, and so on. And now we have to go beyond the probability. We have to talk about logical probability. There's the truth tables, the arguments. There's a lot of logic here. So it's a very complicated problem. Intellectually, it's very interesting, but it's very complicated to build theory. And now the other thing is that I think today most people would be persuaded that it has to do with like synthesis language and so on. I think, you know, machine learning, NLPs, and more, and the transformers could do a pretty good job. But what I'm trying to do is I'm trying to build a theoretical framework. So I don't want just to use machine learning on that. With, of course, machine learning, we have to use it. And even certain things we can use. We have tried certain things with categorical quantum mechanics to do with NLPs, but still, we cannot do a lot of theory. Now, there's another thing where meaning enters into the game is the more philosophical thing, you know, because in Wittgenstein theory, meaning is used, basically. Meaning is context. So in a way, the context or the goal that we have gives some kind of meaning in our work. But what I have to say is that for us, semantic is important. Now, if we go to the microscopic level, I'll go very fast here because I think in the interest of time. The first thing we have to do is that, okay, we have the quantitative perception information. So this has to do with the probability of occurrence. This is back to classical entropy and Shannon theory. So rare events brings more information. Okay, but we have to have this qualitative into the framework, have to bring these qualitative things, which is related to its pragmatic or its value that has for fulfilling a goal. Okay, so what I'm trying to bring here, we have to bring into the probability of occurrence of an event the contextual aspect, or they say the value that it has given its users. Okay, so a first thing to do is to extend the framework that we have, all the nice formulation using entropy. Of course, then we have to deviate from Shannon's entropy, but we can generalize things by bringing weight functions and more general functions and measures actually into the information theory framework. This is a very challenging thing because sometimes we can have good definitions based on entropy about the importance of the thing, and there's many applications in machine learning using beyond channel entropies actually for capturing certain things, for the fixture extraction and so on. Now the problem is, well, what is the operational meaning in terms of communication? Do we have a coding theorem for that and these things? And in most cases, no, but we can still introduce a certain metric that quantifies the importance of a message and resolve basically what we used to do, either capacity maximization problem given some constraints S here, which brings the semantics of information, or some kind of rate distortion. I will say that we are very behind on that because it's not an easy thing, but it's something that could be the foundation, because we're going to have metrics as powerful as entropy to capture importance into the source already. But then there's a lot of technicalities to do. So this is ongoing thing, but we don't have like crisp results, at least with some kind of practical impact for the moment. Okay. Not to mention now that one of the problems we have is that we have time dependence. Time is fundamental in this problem here. So how do we capture time dependent? How do we come with time dependent information? These are kind of challenging theoretical questions. Okay. Not to mention the sensitivity we're going to have on non-stationarities. We're not going to care about the average things. Okay. Now, we could, though, have a more, let's say, pragmatic definition of the importance. And this is inspired by all the stream of work of the age of information. And actually, certain things on the semantics of information came from the age of information community. So what we can do, we can say, okay, information has two kinds of attributes. Okay, it has the inherent ones, the innate ones. So how fresh it is, the precision that I have in a certain measurement, how accurate it represents a certain event. And it has the contextual attributes, which depends on its user. For example, the timeliness. Did it arrive on time when I really had to take a decision? Okay. It could be fresh information that arrived late. Information has a certain age, let's say, a certain freshness, but when it's going to arrive for a certain decision making, you have a different value. How complete is the representation of the event, and so on. So we can think of having vectors or of these kind of attributes, okay, and then bring this into a general function. Now, on the top of that, we have what is the perceptual quality, which depends on the goal. At the end of the day, we have different attributes of information, so we have to define each attribute in a certain kind of formal mathematical way. We have done some of them, okay? But at the end of the day, what is important or what is valuable, it depends on how the observer, how the receiver or the end user perceives actually the transmitted information, okay? And this is a different constraint, this semantic quality that could be measured with some kind of divergence function. I will talk a bit later on that. Not to mention also that the notion of information value has a certain dualism, because certain things could have an inherent attribute, so the accuracy of a measurement, it would always remain the same. But then the accuracy as a contextual argument is like a measurement of the temperature, I don't know, in the first decimal will always remain like that. Now, it could be useful when I do some kind of typical, I don't know, the temperature of the room, but it could be useless and not accurate if I have to make a decision on a nuclear plant. So depending on the context, change this value, although it's the same attribute, okay? So this is also an extra complication. But long story short, we can have some kind, inspired by the age of information, a kind of general function for the semantics of information, which is going to be a nonlinear function of these different information attributes, okay? We can also see it as a multi-dimensional function where you can see it as tuples, basically, okay? And then you're going to have a context-dependent and cost-aware function on the top of that. Okay, because different application will be a mixture of different attributes. We don't have to include them, all of them. Okay, just to give you a very simple example. So suppose that we care about only two attributes. The one is the freshness, or what we call the age of information, which is nothing else than the difference between how much time has elapsed from the moment we receive a packet, but when it has been generated, okay? And this is different than the delay that normally people, at least in the communication physical layer, we care, okay? Why is different? Because you might have a very good transmission channel. We have like, I don't know, an optical fiber versus a very, very slow connection. But if the information that you transmit on the optical channel has been generated yesterday, where the slow connection has been just generated now, when you're going to receive it, if you're going to receive with a large delay from the slow connection, still the information for the decision maker is going to be fresher, probably, than the one from the optical fiber that comes from yesterday. Could be even obsolete, actually, okay? So this brings a new kind of dimension for the information. But suppose also you care about the accuracy, the distortion that you have, like a mean square. So then you can put that on a certain kind of multiplicative function, and then you define the timeliness. So you say, okay, as long as I receive the packets within that window, my interest, my utility is the same, and then it's exponentially decreasing, for example. It can be also you have application which is very, very critical, and you have to receive the information on a specific time instant, not earlier, not later, because sometimes it changes also the design from the over provision. Like, let's say, okay, I have solving the problem with deadlines. So if I receive the information earlier than the deadline, I'm happy. No, there are applications where the information remaining there is going to become obsolete and so on. Anyway, this definition is kind of a generalization of all the existing definitions of value of information, quality of information, age of information, and so on. Okay, so this is things that we can work. We have done a lot of work. I just represent one of them. Suppose that you have different sensors that the observer set a phenomenon, and we have the first importance depends on the probability of the realization. Some sensors are interested to the rare event. Some sensors are interested to the most likely, most useful, most high probability of occurrence event. Could be like two modes, the normal mode, the alarm mode. Okay. And I want to do some kind of source coding so that at the end, when I receive this information to the monitors, I will have fresh information, and also very important. So my utility function, the semantic information was going to be just a function of the freshness, okay? So I could also put some feature extraction. I can also censor some irrelevant realizations. I can also see that I don't have to retransmit, because sometimes I will have realizations that they are not more important than the one I'm trying to send. So there's no point even sending, okay? Because I won't change the utility function. Long story short, by doing some analytical, and I can point you to the papers, I've seen that, for example, if you want to maximize your utility function, actually minimize here because we revert the problem. Suppose that you have a certain number of packets that you have transmit anyways. If you do the traditional approach, okay, there is information, there is an event, there's a realization, then I'm sending in, and it's the observer that decides. Now, by doing all this semantic kind of filtering, we can, and find the source code and so on, we can just bring it back to, for 100 packet, 100 realization, you just need, depending on the arrival rate, to send around 10 of them, and you do your job. Actually, that's the thing. You get the best utility by sending way less packets than what you have done in the traditional approach, when you don't care what you transmit and for what reason you transmit. Okay. So another example we did, I'm not going to go into the mathematical details. Suppose that you have to do some kind of real-time tracking. So you have, I don't know, a robotic arm here, which can be modeled as a very simple Markov source. Let's take a two-state Markov source. We have extended that. I'm going to transmit it through an eraser channel, and then I want to reproduce the state of the Markov source here, because whatever the robotic arm does in the source, the transmitter, I will have to reproduce it at the destination, where I will have to do some kind of actuation. Okay, so basically, what I have to do is that on a real time, I will have to have this, the same state both at the source and the destination. Okay, and we can define two metrics. We can have the real-time reconstruction error. So anytime I'm not in the same state, then there's an error. and there's a cost for that, and the cost is not necessarily commutative. So there is a different cost to mix state 0 for 1 and the 1 for 0. The typical example, traffic light, you don't have the same cost by misinterpreting a green light for red, okay, and then you just brake and then you impede the traffic, versus you take the red for green and you accelerate, probably you have an accident, okay? So it has different costs, okay? Now you see that now is a real time, this indicator function here. It's not the average thing. It's not things that are known. You just minimize the mean square error and then the robotic arm will do it. Well, I don't want to do any hit. Suppose that you have an arm hitting left and right. You always have to hit the left and right according to what the source is doing, okay? Now, typical approaches will have been do some kind of uniform sampling of the source, some kind of, depending on the age, how fresh is the information, or whether the source has changed. If there's no change in the evolution, in the state of the system, then I do nothing. And this is a semantic approach, which basically tries to generate a packet only where there's a discrepancy between the two sides. Okay, you need to track, of course, the changes in both in transmitter and receiver, and then when there's discrepancy, you generate the packet. Otherwise, you don't do. And of course, you have to do some kind of joint. This comes the joint part of, you jointly design the sampling and the communication, because you can sample something, but if your communication channel has errors or is occupied and so on, it has a ratio, then you could have waited actually, not send the packet. So suppose now you have this kind of strategies. So the ones we're interested, the semantic, just to see, even the change aware, the yellow one is considered as kind of a proxy of semantic. But you see how much you reduce the reconstruction error for when you have a high probability of success, 0.9 here, for a change for a source that has traditional probabilities 0.2, 0.7. Okay, and the cost of actuation is the same. Now, what is more important is not only that you go that low as compared to, I don't know, uniform sampling, or whenever you want to give even fresh information to your source. Not only you go that low in terms of reconstruction error, but you send less than 1% of information sample. Actually, in some scenarios, you don't send any packet that is useless, actually, okay? So all the time you send packets that they will reduce your real-time reconstruction error. So this is all the saving that you have in useless packets is saving in energy, saving in computation, and saving also in opportunity. You maximize the opportunities of somebody else can talk. And that's why this is a scalability problem. That's why you could even have more and more things. Now, checking the time, just not to, yeah, I think we're going to be on time. So now I will switch to some different kind of view of the problem in a more general way. So here I have the typical rate distortion problem where I have a source, okay? Normally I compress it, I have the encoder, I do the encoding, I'm sending, and then I'm trying to reconcile with a certain kind of fidelity. Okay, there's a distortion criteria, and I want basically, given a certain distortion I want to achieve, I want to lower the rate I will have to transmit. So basically compress the source as much as possible. So I want to minimize the mutual information that I have between X and X hat, subject to distortion constraint. This is classical rate distortion constraints, the rate distortion theory. And what we call here global grossing is that I don't care why I will use these, let's say, high SNR or low mean square error picture. I would just want to do that, okay? This is the way we're doing tradition. Of course, later you can also put channel here with noise and go for joint source channel coding. Now, there were examples from the computer vision community where you have these two pictures, okay? So suppose that you want to detect the pedestrian here, or you do something with this building. So you're going to choose the upper set of pictures or the lower one. Most people, I think, will agree that the upper one is the one that users will perceive as better to work on or to make a decision upon. Now, it turns out that the upper one that has a very good perceptual quality, these are the high distortion pictures. These are the low SNR pictures. The high SNR pictures are the ones that have the bad perceptual quality. So one thing that was clear in the community on vision and image processing back in the a few years ago is that the good perceptual quality does not implies low distortion. Okay, the same way goes also when we have generative pictures. It doesn't have, you don't minimize the distortion with respect to the existing ones. It's a different story. And this brings a different scenario, which is an extension of the ray distortion, what we call ray distortion perception, but you can see the perception as this semantic quality constraint I was talking about before. Because basically you have a semantic source, you have a very, very high dimensional or even messy concept, whatever it is, which you observe, you take observation of that. You might not even have access to the entire semantic source. You might even have access to where your data lies, or even you might comes from a very high dimension distribution that you don't know even to communicate. You don't even know how to do, sampling. So then you're gonna, this is what the application actually all the way does here. That's why I put the layer here. Now, you're gonna have a certain observations. This is the X. We have a certain distribution P of X, which of course you have to bring it all the way to the observer, which will care about how natural is the picture, let's say, or how good is the perceptual quality or the semantic quality. And this is the X hat, which will belong to this PX hat, it has a certain distribution. On the top of that, you're going to have also the semantic source and how well you represent. So for example, a typical example I give is like, it's different to when you care about the, I don't know, certain summary, to understand a book, you can just take chapter by chapter, do the optimal compression, bring it to the other thing and put them together. Or you can have a smart reader, which will read and make a very nice executive summary and transmit this information. For you as an observer, you might be very happy with that. Actually, you don't have to read the optimally compressed chapter to have the summary of the book, okay? It's kind of a motivating example here. So what we have technically to do is to go one step beyond of the classical ray distortion and add an extra constraint here, not only on the semantic source, this is a distortion constraint, but also bring the constraint of the semantic quality. And this constraint, as I said, is a divergence because what you care is have proximity not on its sample. You don't want to minimize the distortion sample necessarily. What you want is that the picture that you will generate at the destination is looks natural and has good perceptual quality as it belongs to the distribution. This is similar to what generative models actually are doing, or the deepfakes we have with the GANs and so on. And this is because what you want is that the PX, the distribution where your semantic content comes from, is as close as possible to the reconstructed one. So you want to have PX and PX hat, the two distributions, as close as possible. And you can do it by minimizing some Wasserstein indices, some M divergence, these other things. So this kinds of extends non-trivially the ray distortion, and this brings certain semantic quality constraints, and some of them are, you can achieve them or not, but technically this is a more difficult problem. So we have some nice work on that, a very recent one, which is a first step trying to bring these perceptual constraints into the picture, okay? Now, I think I have like 7 minutes or something like that. So what is the bigger picture actually? Okay, because now I give you a few examples that you can work, and there's a lot of technical work behind that. Now, the bigger picture is that, and here comes a connection with the machine learning. I have a semantic content which could lie on a high dimensional space, okay, some complex data. On that, first of all, this I cannot even communicate. I don't even know how to calculate mutual information here. I would need even a neural estimator. What I can do is I could do some kind of low dimensional representation, some manifold matching on that. Okay, could be of course some distortion here, but we can manage this. Based on this, I will do some sensing, pre-processing, encoding, all what your favorite techniques. Okay, you will transmit over the channel. This is the communication problem and reconstruct it. But at the end of the day, what you want to reconstruct is the semantic content. Okay, so this is kind of a generative content. Things where what you care is at the end of the day, is this picture represents what the semantic, what the event is trying to communicate. If I can make reliable decisions, if it has the fidelity or the importance where I care, then I'm done. I don't care if I use the optimal encoders, decoders, and so on, okay? And this brings a lot of ideas from generative models. So this is a communication problem, actually. And the other one, you can model as an optimal transfer problem. This is an ongoing work. And for people like Smuts, actually, at the end of the day, you have a certain distribution here that you have to bring on the other thing. And you have to bring it in an optimal way with the lower cost, but also the representation should be the most representative or the most important for the application, okay? And there's a lot of mathematical things we can play here and generalize a lot of concepts of the radius social perception, even on topological spaces, okay? Of course, that's one. Most things I presented is on a link-to-link, point-to-point. The problem is when you have to bring in all the networking things, and this is where we need all that stuff so that it scales. You need to have the semantic ideas and all these importance-aware things into the multiple access, into the resource allocation, so on. And there's a bunch of things that you have to change into your network. So you have to do it. For example, in the typical multiple access, random access scenario, you don't have the probability of occupying the channel or sending information based on what the source is doing. It's based on the importance that you have. You have to change that and so on. And as I say, the problem here is a non-separable approach. So certain things have to be done smartly, otherwise it's going to be a huge optimization problem. It's going to be a mess. Okay. So in the interest of time, I will skip that because the next slide I could summarize this. What I say in the beginning is that actually semantic communication, this kind of things allows us to do different things. It redefines the effectiveness. So why I communicate and how I can do it more effective by saving actual resources and so on, sending only the information that do the business, actually do the job. But the other underlying thing is that the timing aspect is very fundamental here. It's actually probably the key to solve most of these things. And sometimes timing is related to the effectiveness. So all these things together plays a big role, because actually semantic information is relative. So whatever is important, it has to do with the context, has to do with the evolution that you have in the observer, has to do also with the interactions between the nodes. Okay. Now this brings into the macroscopic thing, which I have only one slide because this is, let's say, the most futuristic part, but for me is the most interesting. So information is relative. It depends actually on who is using it. Okay. So it depends on the observer, and it depends also on the evolution of the two systems. So as I said in the beginning, the macroscopic thing was like the fundamental purpose, like there is an information here at point 8, the physical world, for example, that's generated certain coordinates at a given time, actually. And you want to reproduce it, you want to use it for decision making in your virtual world in a different point in space at a given different time. And here you can do your favorite engineer. It can be a multi-hop thing, a few networks, so on. So use the maximum compression rate you can do to represent this event, actually. And do your best engineering. Do we have the fundamental, actually, can we find the fundamental limits of synchronize the two ends? Because imagine two systems that they operate and it evolves in a different way. Okay, and this brings the idea of that we have to be able to synchronize these two ends, to be able to do things in a real time, even on the metaverse, on digital twin. We have also to have some kind of frame of reference as we had in relativity. Because you can imagine, I will give you a very simple example. It's very more simple than this one, but you understand. So a big assumption we have is that the clocks are, everybody use the same clocks, fully synchronized in all over the networks, and they are with no error. Imagine now that I'm trying to see how useful is the information based on the age of information when I have a timestamp generated by a certain clock at the observer A, at my source, and measure on a different clock, okay, there, which suppose for different reasons, because there is some kind of, you don't have to go to relativity when I go to space and high speeds. You can find just a clock which is a cheap one or has a certain problem in the crystals, and then basically adds an offset. These two ends will measure differently the time. Okay, so time is actually relative here. So when I have to make decisions based on the freshness, or when I have to decide about sequences of events and so on, if I don't have a common reference frame, then I will not have even the same perception of the event, of the reality, and so on. So basically, since we need to use all these frame of references and use these notions, we actually are getting inspired by the framework, the analogies, and also the mathematical framework of relativity to bring these ideas into basically the general problem, which is this information transfer. Okay, because you have to redefine whatever it has to do with time, synchronicity, and when can we say two events are synchronous? When I have to do the decision on different points. Okay, so the previous thing is about the real time as well. This is I'm almost done. So suppose that real time, most people believe it's live. So real time is whatever I can see now, for example. But if an event is created in Mars and somebody's sending for Mars, I'm going to receive it after a lot of time. When I'm going to receive it, is this real time? Yeah, is this what I have as a perception of the event that happened in Mars? Depends on where you put your reference. Okay, so the notion of simultaneity and synchronicity has to be redefined in communication systems. And for that, we need a new framework. And there is some first work on that, actually, in some information theoretic approach of certain things. So this brings me to the end. What I hope I persuade you is that, okay, the new challenge now in the networks is that we have to have wireless communications to support the connected intelligence, all these networked autonomous intelligence systems. And we have to have real-time communications and autonomous decision-making. There's a lot of things to be redesigned, and even the theory has to be enriched. We need to change the way we do it. It's a communication paradigm shift, actually. And I hope to persuade you that this goal-oriented semantic communication, which redefines importance and timing, is the right way to go. There's a lot of things to do. But now the gains, even for an optimized scenario, what we're seeing, and some of these have been implemented. I have colleagues that have implemented on the transport layer, so on. They see real gains in the network by this semantic approach, semantic aware approach, is that we reduce the energy consumption. We don't have to, the computation efficiency is better. Not all these shows, because basically what we try to do is that we don't send useless traffic, actually. Now, it's not you send traffic, you do your engineering, and then the application tells you, oh, that's useless, send me again. You do other things. Okay, this is what we call the minimalistic approach. And this is what allows, on the top of that, scalable systems. So if we want to have scalability in some kind of, I don't know, control, real-time, autonomous systems, probably we need a new theory of communication, and that's the way to go. And there's a bunch of interesting theoretical problems, and people who are interested, I can tell you that, which will allow us actually to bring all these socially useful services. Thank you very much. And I would like to acknowledge, of course, the European Research Council for the support of this work. We started 2.5 years ago. I mean, I started earlier, but the funding. So we're in the middle of the project. And there's a lot of exciting things to do and a lot of challenging theoretical problems before bringing that all the way to the application. Of course, there's a lot of other work that I didn't mention that we're doing. But for people who are interested, I'll feel free to discuss. Thank you very much.
Thank you, Marius. Thank you a lot. On a encore un peu de temps pour quelques questions. Je ne sais pas si dans l'assistance, cette présentation amène à des propositions d'échange. On n'a pas beaucoup de monde. Là, il y a combien? Une vingtaine de personnes. Les gens, comme on avait calé 14-15 heures, il y a des gens qui risquent de partir.
Mm-hmm.
Est-ce que vous avez des questions? Faisal.
Oui, bonjour, merci beaucoup pour la présentation.
Bonjour.
Très, très intéressante. C'est plus une curiosité qu'une question. Sur l'une de vos slides, vous avez mentionné comment il est possible de mesurer la qualité d'une de la sémantique en utilisant une divergence entre deux distributions des données. Je ne me rappelle plus du numéro de la slide, mais de ce qui a été montré, cela suggère qu'on dispose déjà de certaines métriques, comme par exemple la précision. Non, c'est celle d'avant, je crois. Là où il y avait la divergence entre deux distributions, où il y avait l'accuracy, des critères, des attributs, des variables qui relèvent du contexte et d'autres qui... Et en fait, ma question... Non, celle... alors, pardon. Oui, c'est celle-là, oui. Merci. Oui, c'est ça. Et donc là, cela suppose que la divergence, elle est calculée entre deux distributions et chacune des deux distributions, elle est construite sur un espace d'attributs qui, là, par exemple, on voit la précision, l'accuracy pour les attributs intrinsèques et pour les attributs de contexte, il y a la complétude, l'accuracy. Ma question ou ma curiosité, est-ce que cela suppose d'un point de vue machine learning que l'algorithme marche bien et qu'il arrive à délivrer, qui arrive à tourner avec la précision voulue, qui arrive à déterminer, à bien encoder le contexte? Est-ce que c'est bien dans ce sens-là ou...
Bon, il y a plusieurs contextes qu'on peut travailler. Tout d'abord, on peut dire, bah, j'ai une source, j'ai un phénomène modélisé par une source d'information. Donc, si je connais la distribution, bah, les sons sont simples parce que je connais en fait la distribution de l'échantillon. Après, chaque échantillon que je prends, chaque réalisation a un certain attribut d'information. Ça me plaît pas, je l'envoie pas. Mais après, à la fin, je connais la distribution à laquelle je dois converger. Et donc, je peux mesurer la distance. Il y a des problèmes, et ça devient plus intéressant, où je vois un phénomène, j'observe un phénomène physique, je ne connais pas la distribution, je l'apprends. Moi, je connais la distribution empirique.
C'est ça.
Ou je suis dans un contexte machine learning, ben, j'ai un certain somme de données sur le training set qui définit une distribution, mais après, peut-être c'est pas la vraie distribution, mais c'est un ensemble de la distribution. Et l'hypothèse qu'il a, c'est que je peux connaître un peu la distribution empirique. Mais ça, je peux le faire au fur et à mesure, par exemple. Si je prends des échantillons, bah, je crée en fait les distributions empiriques. Après, plus d'échantillons j'en ai, plus proche à la vraie source, je serai. Mais après, je peux avoir l'empirique. Le point ici, c'est que si je vois échantillon par échantillon, paquet par paquet, par exemple, ou réalisation par réalisation, je peux dire, ah, c'est des réalisations. Ou ça me dit qu'il faut allumer quelque chose. C'est très important. Il faut que ça arrive très tôt, etc., etc. Je peux dimensionner mon réseau. Mais il y aura des applications où à la fin, ça ne sera pas des réalisations spécifiques. Ça peut être qu'à la fin, qu'est-ce que je veux, c'est je veux créer en fait à l'observation quelque chose qui ressemble en fait c'est que l'ensemble de échantillons mesurés à la source peut me donner comme décision l'interprétation de ça. Et donc, si je veux générer en fait quelque chose de similaire, je peux le faire en minimisant en gros la divergence entre l'échantillon créé par la source et l'échantillon que j'aurai à l'observation. À la limite, pourquoi ça ressemble les GANs, le Generative Assembling, ils font à peu près la même chose. Je crée des images, les deepfakes, des images des gens en apprenant implicitement la distribution des images des êtres humains. Mais on peut le voir différemment aussi. On peut le voir, par exemple, je vais transmettre, je sais pas, dans un match de foot, je peux transmettre les buts, par exemple, qui met la France à la finale. Ok. Il y a la partie, l'événement que c'est unique, par exemple, les vidéos avec vraiment quelqu'un, Mbappé qui score, par exemple. Et après, il y a le reste, que ça peut être même généré. Parce qu'en fait, je ne suis pas intéressé de voir le vrai supporter qui sont excités, etc. Ça, je peux même le générer, mais il suffit sur certaines contraintes de fiabilité dès qu'il me ressemble naturel. Ça, je peux
Oui.
le faire en minimisant, par exemple, certaines divergences et générer du content offline, par exemple. Il y a plusieurs façons de le voir.
Oui, le point, c'est juste, Patrice, si j'ai encore 30 secondes, le point, c'est, je suis assez d'accord, mais nous, par exemple, dans des use cases industriels, pour construire la distribution empirique, de façon empirique, des fois, ce n'est pas si simple que ça. Par exemple, pour le cas d'exemple, c'est Mbappé qui marque, ça, c'est quelque chose qu'on arrive facilement à voir, mais par exemple, pour des images, pour détecter des anomalies dans une scène industrielle, c'est difficile d'avoir l'ensemble de ces attributs pour dire là, par exemple, une panne ou un obstacle sur un rail à cause de la neige, je ne sais pas quoi. Ça, c'est quelque chose que l'algorithme de machine learning qui a des fois du mal à retrouver. Et donc, la distribution empirique, c'est une question de la construire ainsi. Voilà, c'était un peu pour
Oui.
pointer cet aspect.
Oui, parce qu'en fait, ce sont de rare events. Donc, il faut aller il faut aller vers la queue de la distribution. Donc, il faut changer un peu, peut-être probablement les méthodes, parce qu'apparemment, il faut aller dans la partie de la distribution qu'en général, les méthodes un peu conventionnelles ou classiques ne marchent pas très bien. Mais il y a des travaux sur ça, en fait. Mais oui, ça vient parce que c'est du rare events. Donc, c'est des outliers parfois ou de anomaly detection, non? C'est ça. Et dans
Oui,
ces
c'est ça.
cas-là, en fait, je n'ai pas besoin d'une divergence, parce que dans ces cas-là, moi, je sais que je peux dire, supposons que j'ai un capteur qui fait ça, donc je ne veux pas mettre le capteur qui émet de contenu si ce n'est pas un rare event, ce n'est pas une anomalie, par exemple. Je peux de temps en temps envoyer que tout va bien, mais faire, sans savoir que je veux faire une anomaly detection, que j'envoie la mesure d'un certain indice que j'envoie de temps en temps, je consomme des ressources ou le réseau pour rien, en fait. Parce que moi, ça m'intéresse, par exemple, quelle est l'anomalie. Pour le reste, donc c'est ça qui change, en fait, dans la communication. Au lieu d'envoyer après l'observer ou le responsable dit, j'ai rien à faire. À chaque fois qu'on recevra d'informations, il n'y a rien à faire. Après, ça ne veut pas dire, en fait, qu'on n'envoie pas beaucoup de contenu. Quand il y a une anomalie, très probablement, il faut envoyer avec beaucoup de rate et tout ça. Mais en moyenne, on gagne sur le trafic. Mais ça suppose, et même le capteur, peut-être, il n'observe pas la source s'il n'y a pas une anomalie. Il y a d'autres indices que dire, s'il n'y a pas d'anomalie, il ne faut même pas être, il faut l'éteindre, en fait. Mais ça suppose qu'il connaît, en fait, le but de la communication.
Merci
C'est qu'il
beaucoup.
impose, en fait, une espèce de signaling qu'il faut. Ça, c'est la partie ingénieure du concept. Mais ça peut changer, en fait, le débit qu'on a besoin, la batterie du capteur, tout ça, si je connaissais que, voilà, ça m'intéresse une anomalie. Donc, pour le reste, c'est rien. C'est
Ouais,
un peu ça la sémantique.
on va essayer de passer à une autre question, si je m'excuse, parce que les gens vont
Oui,
risquer de
oui.
partir. Je crois qu'il y a Inès qui a levé la main. Je ne sais pas si elle est encore connectée.
Oui, je suis toujours là. Vous préférez bonjour, vous préférez en français ou en
Bonjour.
anglais? Oui. Bon.
Français,
Merci.
anglais.
Okay, thanks for the exciting talk. It's really very interesting. So my question is more about protocol engineering vision. Like, do you think that we need to rethink the communication stack, not layer based, more cross layering, or maybe monolithic function? Because if I understood well, the service. Finally, it's the service. What you call you were talking about goal, but for me, it's service driven. So, do you think that we need to abandon or ignore all the classical metrics, delay, things like that, reliability, number of packets, and so on, and concentrate more our performance metric on the application level, on the service level, like accuracy, precision?
Yeah, thank you for your question. Excellent question. Actually, what I'm presenting here is the theoretical part, because this is the ERC kind of thing. But I've thought about all these things. So one thing that probably implies these kind of things, if we show high gains, well, we have to challenge even the Aussie layer, because at the end of the day, you could see it, as you said, this is like a cross-layer approach. Okay, but basically what you do, you hardwire the application layer all the way down to the physical MAC layer. Okay, yeah, exactly. And actually you could do things transparent on, layer 3 and so on. But yeah, it will challenge the classical layering approach. Now, people from upper layers in networking have already touch similar ideas, like for example, the name data network, the intent-based networking goes toward that perspective, okay? But definitely, if we want to implement that, we'll have to challenge the classical layering thing, definitely. Otherwise, or somehow, but then we'll have to see whether this is going to kill ourselves in terms of signaling. You have to bring all the requirements and as kind of functions or metrics of the application layer all the way down, and the goal, so that even a small, tiny sensor in the middle of nowhere in the network knows that. The signaling could be huge. So probably the only way to go is that some of the things you change the layer. So yeah, the protocol design that we have to do, if we are persuaded that the gains are high, we need to do it. It will reopen the protocol stack for sure. You want to have or you have a different layer, the semantic layer, working in every kind of, together with every kind of things in the stack of your ROSI layer, if you want to do it that way. But definitely, yes.
Thanks.
Does it cover your question?
Yeah, definitely. Could we have the slides or?
Oui,
I can send it to Patrice, and there's no
yes,
problem.
yes, we can put it on the side. J'avais une petite question, Marius. Je me suis, en regardant tes slides et en t'écoutant, j'ai pensé aux auto-encodeurs qu'on utilise en traitement en ce moment, beaucoup en IA générative, et je me suis posé la question si finalement, quelque part, de chercher l'espace latent pour finalement opérer une communication dans cet espace latent plutôt que dans les espaces d'origine, est-ce qu'on n'aurait pas un gain? Est-ce qu'il y a des travaux qui travaillent là-dessus, sur la communication dans les espaces latents? Enfin, question tout à fait ouverte et peut-être un peu idiote, mais
Non, non, pas encore en fait, parce que le problème, c'est qu'en général, en télécom, les gens qui font la théorie, en général, c'est des sources simples. C'est toujours un variable aléatoire, gaussien, etc. Ça, on sait le faire. Après, si on commence à compliquer un peu la sauce, même les entropies, mutual information, tout ça, pour optimiser, on ne sait pas le faire. Donc, soit on va choisir à travailler sur un autre espace, soit, par exemple, l'espace de latence, ça peut être une chose. Soit on va utiliser l'espace latent comme information complémentaire ou à côté pour améliorer la façon où j'envoie, où je reçois, en fait, où je traite, en fait, je fais le décodage. Donc, on peut dire, par exemple, que l'espace latent peut-être nous montre la sémantique ou l'importance de certaines choses. Je peux l'utiliser comme side information. Il y a des idées, mais en général, on n'a pas encore fait. Pour l'instant, on fait la théorie. Comment je peux, si j'ai d'échantillons, envoyer toute la distribution, etc. Après, on n'a pas joué encore sur les approches un peu machine learning, parce que pour l'instant, je reste dans l'approche un peu théorique. Mais après un certain moment, on va avoir les murs pour le truc formel, même algorithmique classique. Et là, on va faire tout le... Il y a aussi beaucoup des outils qu'on s'inspire du manifold learning et tout ça. Après, même le problème dans quel espace, par exemple, je pense tu parles de ces slides, en fait. Même ici, quand je fais de l'espace comme ça, on peut le voir comme un ray distortion problem.
Oui, bien sûr.
Il y a une certaine distorsion à faire ça, et ça, on peut le faire. Il y a quelques travaux, et maintenant, on commence un peu à capturer ça. Mais après, est-ce qu'on garde la géométrie, hein? Donc, toute la topologie qu'il faut prendre pour faire une représentation de l'information, c'est maintenant qu'on démarre, en fait.
Ce qui est un peu compliqué, c'est qu'il faut envisager des versions online de ces algorithmes, puisque l'espace latent, il passe son temps à bouger dans une communication. Et donc, ça veut dire qu'il faudrait trouver des algorithmes pour la mise à jour en continu d'un auto-encodeur pour bouger l'espace latent et que le channel travaille dans cet espace latent de façon prioritaire.
Ouais.
Et il y a un algorithme de poursuite, il y a un truc de poursuite à faire.
Ouais. C'est compliqué. Et en fait, si vous voulez un peu les résumer, c'est aussi été un peu choquant pour les reviewers quand j'ai écrit. Moi, je venais d'une thèse de couche phi, donc en général, j'étais connu plus pour couche phi ou géométrie et d'autres choses. Et en fait, dans tous les problèmes, la partie communication comme pure dure couche phi, je pense que c'est pas très important parce que peu importe les couches phi, les problèmes qu'on doit résoudre, c'est ailleurs. C'est sur les côtés, sur la reproduction, parce que même parfois quel flux d'informations il faut reproduire. Parfois, on ne veut pas l'entier et tout ça. Donc, il y a moins un problème de communication. Commence à toucher un peu tous les problèmes qu'il y a dans le machine learning, etc. Sans être une approche machine learning, ça c'est clair. Il y a certains qui disent qu'on fait que du machine learning. Non, il y a encore du théorie à faire.
Ok. Ben, on va être obligé d'arrêter là parce qu'on a d'autres contraintes pour beaucoup de participants. Merci, merci beaucoup, Marius, pour cette présentation tout à fait
Merci beaucoup.
instructive et didactique. Enfin, c'est vraiment, j'ai beaucoup apprécié. Je pense que je ne suis pas le seul. Et je te dis à bientôt, à une prochaine fois peut-être.